Hey everybody, welcome back to Chem 103 lecture. This is Chapter 8. If you're watching Chapter 8 and you're like, "Hoo boy, how much more do we have to go?" Not that much more. Chapters 8, 9, and 10, and then the semester's over. I'll give you a little bit of a preview of what's to come. So in this chapter, we're talking about the mole concept. We're building our skills so that Chapter 9, we can talk about chemical equation calculations, also known as stoichiometry. Chapter 10 is going to be on gases, and we're going to include a little bit of what we've done with the mole with our gases as well. So, all of these things build on each other. If math isn't really your thing, make sure that you get help early. It is not impossible. It may be a little more challenging, but it is not impossible. Get the help you need, gather your resources and your support, use tutoring, office hours, study together safely. Everything that you need to do to be successful, do it. Get everything lined up and do it. Alright, let's get started. Avogadro's number. This is a number that you will see a lot from here through the rest of the course. It's the number of atoms in 12.01 grams of carbon. Know this number. On your exams, you're not going to receive an equation sheet that says what Avogadro's number is. You need to know it. And his number is 6.02 times 10 to the 23rd. Avogadro did work with gases, and we'll see him crop up again. The mole is a unit of measure for an amount of a chemical substance. A mole is 6.02 times 10 to the 23rd particles. What does particles mean? Well, it can mean atoms, it can mean ions, it can mean molecules. 6.02 times 10 to the 23rd atoms, ions, or molecules. That's what 1 mole is. So if I have 1 mole of sodium atoms, that means I have 6.02 times 10 to the 23rd atoms. If I have 1 mole of oxygen molecules, remember O2, it's a shout out to Chapter 7. If you don't remember that, it's a diatomic molecule. If you have 1 mole of oxygen molecules, you've got 6.02 times 10 to the 23rd molecules. The way that I like to talk about the mole, it's very similar to saying you have a dozen of something. If I say, oh yeah, I'm about to go to the store and grab a dozen eggs and a dozen cookies, you know that I'm going to come back with 12 eggs and 12 cookies. A dozen equals 12. Doesn't matter what you have 12 of, cookies, muffins, eggs. Doesn't matter. You know that dozen means 12. In this case, this is kind of like the chemist's dozen. A mole is 6.02 times 10 to the 23rd particles. Now, how can we use that? Well, what we're doing in this chapter is we are building our skills so we can do more complicated calculations involving chemical equations. So we're building the foundation in Chapter 8 to learn how to use the mole and a few other numbers. And then we'll combine all of that in Chapter 9 to figure out how much of a product you can make or how much reactant is required. So, what I'm going to do here is break down the different types of questions you can see. Notice in the title we've got Mole Calculations 1, which moles can be abbreviated MOL. We're taking the number of moles and converting that to the number of atoms. You can also put ions or molecules here. How many sodium atoms are in 0.240 moles of sodium? How would you recognize this as a moles to atoms problem without the title? What I recommend you do is you highlight or underline the unit that's asked for in the question. So in this case, sodium atoms. We don't have a number for sodium atoms, so that means that's something we have to figure out. And what we're given is 0.240 moles of sodium. Well, what I'm given, it's got to be the number, right? This is what's given. What we need to know is how many atoms. When you see moles on one side with a number and atoms on the other, then it's a moles to atoms conversion. When you're going from moles to atoms, and again, this applies to ions and molecules too, you have to use Avogadro's number. We know that 1 mole is equal to 6.02 times 10 to the 23rd atoms. This is our unit equation. Then we can write unit factors from this unit equation. So you write 1 mole over 6.02 times 10 to the 23rd atoms. And then you write the reciprocal. Those are our unit factors. If this terminology is a little bit fuzzy for you, review chapter 2. That's where we first brought out unit equation and unit factors. What we're doing here is very similar to what we did in chapter 2, where we're taking one unit and using a unit factor to convert it to another unit. We're starting with 0.240 moles of sodium. We need to choose the unit factor that's going to cancel moles and give us atoms as our ending unit. Moles has to be in the denominator of the unit factor we choose. The moles cancel because you have one in the top and one in the bottom. That means we have atoms. When you enter this into your calculator, you're going to put 0.24 times 6.02 times 10 to the 23rd. You may want to use parentheses around Avogadro's number just to make sure that it gets entered properly. Refresh yourself on how to use your calculator with significant figures. Significant figures we do care about, but with scientific notation. That's what I meant to say. We will be using scientific notation here, so get used to that too. Refresh yourself. When you do that math, you consider how many sig figs we should include, which this number has 3 sig figs. You should get 1.44 times 10 to the 23rd. And that's sodium atoms. Do not forget your units. Just like in chapter 2, units are important. I don't know what that number means if you don't put any units. Let's try another problem. How many moles of tin are in 1.25 times 10 to the 21 atoms of tin? What I want you to start to practice is, once you see a question like that, figure out what's given and what's needed. What is the question? What units do I need to answer the question in? Whenever you see a number, that's your given information. When you see something about a unit but no number, that means it's what you need to figure out. We've got 1.25 times 10 to the 21 tin atoms. And we need to know how many moles. We've got a number of atoms, question mark moles. That makes this an atoms to moles conversion. It's very similar to what we just did, but we're starting with atoms instead of trying to answer the question, how many atoms. We're still going to use Avogadro's number. And the unit factors are still the same. So these are, and I'll label them, the unit equation. Remember, an equation has an equal sign. And our unit factors. The factors look like fractions. When we go to set up this equation, we're starting with the number of atoms this time, and we need to end up with the number of moles. We need to have atoms in the denominator to cancel it out. Atoms cancel. We're left with moles, and that's exactly what we want. When you have a number in the numerator and a number in the denominator, you have to divide. So 1.25 times 10 to the 21 divided by 6.02 times 10 to the 23rd. Your calculator will tell you this number, and that's with 3 sig figs. But what if we wanted to write this in scientific notation? What we would need to do is take this decimal point and place it after the 2. That's our coefficient, because the coefficient has to be at least 1, less than 10. To figure out the power of 10, we figure out how many decimal places we had to move. 1, 2, 3. But we're not done yet. The number we started with is smaller than 0. That means that the power of 10 has to be negative. Some of the questions on your homework or on an exam may specify that you should answer in scientific notation. So if you put 0.00208 moles, that is the correct numerical answer, but it is not formatted properly. So take the time to make sure you know whether you need to use scientific notation or not. I did not ask for that in this question, but I wanted to point it out here. So that is the first kind of mole calculation, taking the number of particles, converting it to moles, or the number of moles converting to particles. Now we'll talk about molar mass. The atomic mass of any substance expressed in grams is the molar mass of that substance. We have the example of carbon. Its atomic mass is 12.01, so the molar mass of carbon is 12.01 grams per mole, and that's what that G/mole is. Remember on the periodic table that there's a whole number above the symbol for the element, and you have that atomic mass at the bottom. The atomic mass at the bottom is what we're looking at when we're trying to figure out the molar mass of a substance. Most of the substances that we're going to run into are going to have more than one element involved. For that, all you have to do is add together the atomic mass for each of the elements you see in the compound. You'll always need your periodic table. What is the molar mass of nitrogen gas, which is N2, another one of those diatomic molecules? Well, the only element that we see is nitrogen, but we have two of them. So we can write this as we've got 2 moles of nitrogen, and each of those moles weighs 14.007 grams. In essence, all you're doing is 2 times 14.007. But I want you to see how it works out with the math and the units. So 1 mole of nitrogen gas is equal to 28.014 grams. Another way to say this is 28.014 grams per mole. Same thing. What is the molar mass of copper 2 nitrite? So we've definitely got a little bit more complicated compound here. We've got 1 copper, and then we've got 2 nitrogens. So let's write this out. 1 copper plus 2 nitrogens plus 4 oxygens. Remember, this 2 here means that I multiply everything in the parentheses by 2. That's how we got 2 nitrogens and 4 oxygens. I'm going to write out oxygen here so it's not confused as a 0. When you look up all of these on the periodic table, that's copper. And then we have 2 times the nitrogen. And 4 times the oxygen. This is our molar mass. So the only tricky thing here is to make sure that you account for all of the elements in the compound. Once you know how to calculate molar mass, you can use that to figure out the mass of a compound. We can use moles and mass together. What is the mass of 1.33 moles of titanium, which is Ti? So this is our second mole calculation. We've got moles to mass. Let's highlight what we have in the question. The number that we have is the number of moles of titanium, 1.33. We're asked for the mass. That just means the number of grams. We've got a number of moles on one side, question mark with grams on the other side. Whenever you see mass, think grams. This is a moles to mass question. The way we calculate the number of grams in the number of moles we have is by using the molar mass. So the first step is to calculate the molar mass, which I'll abbreviate MM, of titanium. The second step, we're going to use the molar mass as a unit factor to calculate grams. So step one, we need to figure out the molar mass. Since we're talking about titanium, and titanium is just one element, all we have to do is look at the periodic table. Whatever it says underneath the symbol for titanium is what we use as our molar mass. So that's our molar mass, 47.867 grams. To translate that into a unit equation, 1 mole of titanium is equal to 47.867 grams of titanium. We can write out our unit factors. Those are our unit factors. For molar mass, let's use orange. Starting with the number of moles, we choose the unit factor That will get us from moles to grams. That means moles must be in the denominator, so we cancel them out. Moles cancel. We're left with grams. Then you just multiply. 1.33 times 47.867 grams. The number of sig figs that we need here is 3. Do not forget your units. If you don't tell me grams, I don't know it's grams. And if you don't write grams, maybe you don't know it's grams either. And if you don't know it, how can I give you points for it? So show me what you know. Show me all the units. So we're going to build on this second mole calculation here. We can go from atoms to moles to mass. We know that 6.02 times 10 to the 23rd atoms or molecules are in 1 mole. We also know that the molar mass tells us the mass of 1 mole of a substance. So let's put these things together. What is the mass of 2.55 times 10 to the 23rd atoms of lead? You know I like my highlighter. We've got mass, and we've got a number of atoms. They're lead atoms. What's the question? Well, what we're given is 2.55 times 10 to the 23rd lead atoms. That's what has a number associated with it. What we don't know is the mass, which, remember, when the question is asking for a mass, we're talking about grams. We can't just jump from atoms to grams. We have to use moles. So if you think about chapter 2, when we were doing all of those conversions, we had to go through kind of a base unit. We couldn't just jump from kilograms to nanograms. We had to go from kilograms to grams and then grams to nanograms. Moles is like that. You can convert everything to moles and then take moles and put that to whatever your other unit's supposed to be. So our first step is atoms to moles. We always use Avogadro's number. I'm just going to write the unit factors this time. Those are our unit factors. For the second part of our calculation, we're going to take the moles and convert to mass. We'll need molar mass for that. Since we're just talking about lead, lead is an element on the periodic table. You can just look it up and see what the atomic mass says and just express that in grams. Here are the unit factors for that. Time to set up our equation. We're starting with 2.55 times 10 to the 23rd lead atoms. It's going to be a little bit of a tight fit, but I'm going to try to squeeze it all in there. First, we have to deal with converting the atoms to the number of moles. We've got atoms in the numerator, so we choose the unit factor that has atoms in the denominator. Just barely fit it, y'all, but we did it. Then we have to choose the unit factor that will convert moles to mass, which is grams. This means the unit factor we choose has to have moles in the denominator. Let's look at our plan. We're starting with atoms. This first unit factor should get us to moles. The second unit factor should get us to grams. When we do all of our unit analysis, the first thing that we end up with is moles. Great. Then we cancel that out and we end up with grams. And that's exactly what we want. When you're doing this calculation and you're putting it into your calculator, take the number of atoms, divide by Avogadro's number. Then you multiply by 207.2. Don't forget, if a number is in the numerator, you multiply. Number is in the denominator, you divide. We need 3 sig figs here. And that's your final answer. Take your time with these questions. Identify the problem types that are involved to get from point A to point B. Let's try another example. How many fluorine atoms are present in 2.25 grams of fluorine gas? Fluorine molecules. That doesn't have a number. That's what we want to know. 2.25 grams. That's what we're starting with. We're starting with the mass, and we're trying to convert to molecules. We're going to do the same thing we just did, only we're starting with the number of grams. We convert the grams to moles and the moles to molecules. Whenever you're converting grams to moles or moles to grams, you have to use molar mass. The molar mass of fluorine is going to be the atomic mass of fluorine times 2. So there's our unit equation. And then we write out the unit factors. The second part of our equation takes those moles and converts to molecules. Whenever we do this, we use Avogadro's number. There is our unit equation. Avogadro's number is a long number, even when it's written in scientific notation. I could not imagine having to write out all those zeros every single time. Talk about grateful for scientific notation. That is me. Now let's put our whole equation together. We're starting with the mass of fluorine gas. First, we choose our unit factor that's going to take us from grams to moles. It should have grams in the denominator. Next, we choose the unit factor that's going to get us from moles to molecules. Let's make sure that our units cancel. First thing we did was go from grams to moles. Check. Then we got rid of those moles because what we really wanted was molecules. Check. Take the mass, divide by the 37.996 grams, multiply by Avogadro's number. We need 3 sig figs here. Chances are when you're writing the number of atoms or molecules, you're going to use scientific notation because it's going to be a number that's really, really big or really, really small. We can do these calculations if we just take our time. I want you to see that. They're not difficult. We're just putting together the simple problem types that we've already learned to do a more complex calculation. Here's a question type that you will absolutely see on your exam. No tricks. I'll show you how to do it. What is the mass of a single molecule of sulfur dioxide? The molar mass is 64.07 grams per mole. Didn't even make you have to calculate that. This is a moles to mass question, or a molecules to mass question, excuse me. We got to get to moles eventually. We know the mass of 1 mole of sulfur dioxide. We're trying to figure out a single molecule. I know the number of molecules. It's 1. I don't know the mass of 1. This is a molecules to mass question. It's just strange because it's asking for a single molecule. You can still take that and convert it into number of moles using Avogadro's number. And that's what we have to do here. So we're going to take molecules to moles, moles to mass. That's our plan. For molecules to moles, we use Avogadro's number. I'll just write out the unit factors here. For the second part of the equation, just like in the other mass, molecules to mass question, we need the molar mass. So we're going to take the moles, convert to mass, using the molar mass of sulfur dioxide, which was already given. So we don't even have to calculate it. You can just write out your unit factors. Then we put it all together. How many molecules do we have? 1. We figure out which unit factor we need molecules in the bottom to cancel out. Then we need to have moles in the bottom of our second unit factor so that we're left with grams. In our plan, we've got molecules to moles to mass. We get rid of molecules and we're left with moles. Then we get rid of moles and we're left with grams. Take 1 divided by 6.02 times 10 to the 23rd and then multiply by 64.07. What you get is a ridiculously small number. But it should be very small because we're talking about a single molecule. So if you see that number on your calculator for one of these, what is the mass of a single molecule or a single atom of something? If you see a really small number, that means you did something right. I'm not going to say it's absolutely right, but you at least did something right. Know this question type. It will be on the exam. Last concept for this video. Molar volume. Molar volume applies to gases only. We're going to spend a whole chapter on gases when we get to chapter 10. Molar volume will come back. So make sure that you keep this on lock at the back of your brain. We'll see it in chapter 9 too, but we're doing gases for real in chapter 10. At standard temperature and pressure, which we'll define in chapter 10, don't worry about it for now, 1 mole of any gas occupies 22.4 liters. So it doesn't matter whether it's oxygen, nitrogen, helium, whatever gas, if you have 1 mole at the standard temperature and pressure, then you know the volume is 22.4 liters. That volume is called molar volume. You'll need to know that number. So this whole thing down here for gases, know this. A mole of gas is equal to Avogadro's number of molecules of gas, and it has a volume of 22.4 liters. Let's do some calculations with that. A sample of methane occupies 4.50 liters at STP. How many moles of methane are present? Let's see what we have. We've got a volume at STP. How many moles? The number we're given, 4.50 liters. The question is asking about moles. Whenever you see liters, that's a volume, and we're converting it to moles. That's another simple question type. It's only for gases, but you can take the volume and convert to the number of moles at STP. This is our unit equation. 1 mole of gas gives you 22.4 liters. These are our unit factors. We just made fractions using the unit equation. Now we can set up the actual problem. We need to choose the unit factor that's going to cancel out the liters and give us moles at the end. Our units cancel. We're left with moles. You take 4.5 and divide by 22.4. With 3 sig figs, we get 0.201 moles of methane. We're going to take a little bit of a detour and talk about density. We covered density of solids and liquids, but now we're going to talk about the density of gases because it's related to molar volume. One way that you can calculate the density of a gas is to take the molar mass in grams, divide by the molar volume in liters, and this is at STP. The density of gases is much less than that of liquids, so we're not going to be getting huge numbers here. Let's try it. What is the density of methane gas at STP? Sounds scary, right? Because we don't have any numbers at all. We know we need the density of methane at STP. When you see density and STP, that means that you can use our new little equation. The density is equal to the molar mass expressed in grams over the molar volume. I abbreviate that MV. And this will give us units of grams per liter. Can we calculate the molar mass of methane? Absolutely. You just need your periodic table. So let's do that. There's 1 carbon, and it's 12.01 grams per mole of that. There are 4 hydrogens that are each 1.01. So there is our molar mass. The molar volume is always going to be 22.4 in this type of question. Now, if we were given a certain volume, then it would be a little bit trickier. And we'll do a problem like that, but not here. You have to come to class for that. But when you have the blanket, what is the density of this gas at STP? Always use 22.4. $16.04 grams in the top, 22.4 liters in the bottom. And there's our density. We use 3 sig figs here because the molar volume has 3. So we'll do another density problem type. I'll give you a little sneak peek of it here, but we'll work on it more in class. This type of problem, for whatever reason, it kind of seems more difficult than it is. So we'll do practice in class, but I'll show you kind of how to do it now. You've got an unknown gas. There's a mass of 4.29 grams, and it occupies 1.50 liters at STP. We need to figure out the molar mass. We can absolutely do this, and the reason is we know what density equals. The density of a gas at STP is the molar mass over the molar volume. We also know another definition for density, and that definition works whether we're at STP or not. And that's simply mass divided by volume. So we can calculate the density, which is our first step, using mass divided by volume. Then our second step, using the calculated density, we can solve for molar mass in the, we'll call it the STP density equation. So step 1, we'll do that in green. We were given a mass and a volume in the question. The mass was 4.29 grams. The molar and the volume is 1.50 liters. You can figure out what that density is by simply dividing the two. That gives you 2.86 grams per liter. The second step we'll do in purple. We take our density and say that is equal to molar mass over molar volume. Molar volume, we already know, is 22.4 liters. To solve for the molar mass, you multiply both sides by 22.4 liters. And that's how you get your molar mass. Again, we'll do some practice on that problem type in class. There will be a problem like this on the exam. So we've now got 3 different interpretations of the mole. We've got particles, Avogadro's number, and that can be atoms, ions, or molecules. We know that 1 mole is equal to the molar mass, so that's the atomic mass units expressed in grams. And for gases only, 1 mole at STP has a volume of 22.4 liters. So let's put these together. What is the mass of 3.36 liters of ozone gas at STP? Well, we've got what is the mass? Well, that's a unit without a number. Must be what we need to figure out. 3.36 liters, that's a volume. And we're told that we're at STP. We know the formula for ozone, so we must be able to figure this out using pretty minimal information. We're taking a volume, and we have to convert it to grams. That's a volume to mass question. We have to do a couple of steps here. We go from the volume of the gas to moles. Then we go from moles to mass. I think I did that in blue. I hope I'm right. I try to keep the colors consistent. To go from volume to moles at STP, we use molar volume. That's our unit equation. 1 mole of ozone is equal to 22.4 liters. Then we write our unit factors. The second part of the problem, we're taking moles and converting to mass. you need molar mass here. To find the molar mass of ozone, you're taking what you see on the periodic table for oxygen and multiplying by 3. You should get somewhere in the ballpark of 48. My periodic table has 15.999 for oxygen, so I get 47.997 grams per mole. If you did 48 here, it would be fine. Let's write out the unit factors. These are our unit factors. And you know what's next. We've got to write out the actual equation. We're starting with the volume. And that was given in the problem. Now we need to choose our unit factors. We need to get rid of liters for the first one, so it should be the unit factor with liters in the bottom. Then we have to take those moles and convert to grams. We want moles in the denominator this time. Make sure everything cancels out before you start doing the calculating part on your calculator. We get to moles. Then we get to grams. That's what we want. Take 3.36, divide by 22.4, multiply by 47.997, or 48, because your periodic table may have said 16.00 for oxygen. That's okay too. We'll still get about the same answer, which is 7.20 grams of ozone. That's 3 sig figs here. Our volume had 3 sig figs, so that's what we're carrying forward. How many molecules of argon gas occupy 0.430 liters at STP? How many molecules? That means that's what we're looking for. We also have a volume at STP. What we're given is the volume. What we're trying to get to is the number of molecules. This is a volume to molecules question. Starting with the volume of gas, we can calculate the number of moles. Once we know the moles, the sky is the limit. But we're just going to go for calculating molecules. The first step is going to look very similar to what we just did. Take the volume, convert it to moles. These are our unit factors. And that comes from the molar volume. 1 mole of gas has a volume of 22.4 liters at STP. The second step is taking the number of moles and converting to molecules. So we've got our unit factors for each part of the equation. Now we just need to choose the right one as we're putting it together. Liters needs to be in the denominator here so that we can cancel them out and be left with moles. Moles needs to be in the denominator so we can cancel it out and be left with molecules. Check your units. We get to moles first. Then we get to molecules. Take your volume, divide by the molar volume of 22.4, multiply that by Avogadro's number. You should get 1.16 times 10 to the 22, and don't forget your units. That's all for the first part of the mole concept. Make sure that you watch the second video for the remaining topics in Chapter 8. Again, we split up this chapter. So we focus on this part, just learning how to do mole calculations for the first week. And then the second week, we'll do some more calculations with the mole. Make sure that you tune in for live lecture because we'll be doing lots of practice problems. And you'll get details regarding assignments and exams. Until then, stay safe.